One of the main differences between galactic dynamics and planetary dynamics is that in planetary dynamics, the motion is dominated by a central mass. In the solar system, 99% of the mass resides in the sun. In a galaxy, the situation is reversed. The central supermassive black hole of the Milky Way counts about a few million solar masses, whereas the galaxy itself has over 10 to the 12 solar masses. So clearly, in a galaxy, it is not the central mass that dominates. The stuff in the galaxy, the stars, gas, dark matter, they generate a potential, and stuff moves individually under the influence of this common potential. So let's study potential theory to understand how the motions in a galaxy occur. Instead of adding up the gravity of every single one of the 10 to the 11 stars in a galaxy, we're going to smooth their mass density on a scale that is small compared to the size of the galaxy, but big compared to the mean distance between stars. The potential is computed with this average mass density, and individual stars will be treated as test particles moving in this potential. So to start, what is the force F on a mass m at a position x that is caused by the gravitational attraction of a distribution of mass with density rho? According to Newtonian gravity, the force is obtained by summing the small contributions. So you can divide this distribution of mass by individual parcels of infinitesimal mass dm, and you can then substitute each one of these individual masses by rho times dv, the differential volume, and sum up all the small contributions. We can then integrate this infinitesimals of force to find the full force. And doing that, we can define the gravitational acceleration. And comparing the expressions, then this acceleration is. We can define also the gravitational potential. It's qualified, given by this expression, so that if we take the gradient of this expression, we find the gravitational acceleration. So for that, let's use SymPy. Let's import SymPy, use the printing capabilities, import reference frames so we can deal with vectors, import also the gradient function. So let's define the reference frame. What this function does is that it loads the two-dimensional Cartesian reference system. So we can define now our Cartesian vector x. The zero component is the scale basis x. R dot x is the unit vector in the x direction. So this is x hat. Same thing here for y times y hat and z hat. So this line here translates into xc is equal to x times x hat plus y times y hat plus z times z hat. Okay, so that xc is the little x that goes in here. Let's now define the x prime. The x prime is going to use the same reference system, but we're going to use symbols x, y, and z. And then we can define the x prime. Let's define now the modulus, which is xc minus xp, x minus x prime. This symbol here, the ampersand, means a dot product. Now let's take the gradient. The gradient of 1 over the modulus, and r here is for the reference frame that is calculating the gradient. So the result is, there you go. Rx here is the R0, so that's the x. And what I call here is x prime. So what you have in the end here is, for each component, you have minus x plus the prime. And the denominator in all cases is the cube of the modulus. This expression then, substituting these variables that we use in SymPy, then becomes the simpler expression. X prime minus x over the cube of the modulus. And if we compare this now with the gravitational acceleration, that's what we had here, x prime minus x and the cube of the modulus. Therefore, then we can write the gravity as minus the gradient of the potential. In many situations, it is easier to find the gravitational potential phi and then take the gradient to find the acceleration. Moreover, the gravitational potential is a scalar quantity, so we are exchanging three quantities for only one.